Okay, thanks.
Thank you. Something into the mic so I know. No, yeah, hold on.
Okay.
It's on. We're good.
Oh, okay.
That's okay. Okay.
It's my pleasure to introduce Chih Wei Chang. He defended his thesis in March. Please get him the talk.
Thank you. Thanks for visiting. Good afternoon, everyone. Today, I would like to present part of my PhD work, which is machine learning frameworks for the development of thermal fluid models. And this is an empirical approach. And the whole approach belongs to a data-driven modeling methods. The data-driven modeling method has been previously done by many people, and why we are want to using the machine learning technique to help us to develop a model. The main reason is the previous data-driven technique highly rely on human efforts to tune the model parameters. And when we want to change the model form to capture the new experiments, it will be very hard. And with the help from machine learning methods, it offers a capability to leverage the value from data, and we can shorten the model development time. I will start from the introduction, the motivation, why I want to do this job, and I will provide some essential technical background to achieve our goal. And then the third part will be introduce the machine learning framework to achieve the data-driven modeling for the thermal fluid simulation. And I will provide several applications. And finally, I will address the issue of using machine learning, especially deep learning, for the model development. The subgrid scale physics model determines the accuracy of the thermal fluid simulation. And traditionally, we use the analytical form and rely on the human experiments to tune the model parameter to allow the model to fit the data. Such approach requires a long time for the model development, and that limited the path of model application when dealing with the newly designed system, including new geometry and new coolants. First, let's just take a look. What is causal relations? For people with neutronic background, the causal relation is very similar to the cross-section. Like when we're solving a neutron diffusion equation, the cross-section is essential to help us to solve the equation. And usually, the cross-section need to be coming from the experiments. And if we are interested in diffusion method, then we need to have some transport method to homogenize the cross-section. And in the thermal hydraulics, we have a lot of different conservation equations. And let's take a look at the momentum conservation equation. In this equation, we need the Voigt fraction correlation to help us solve the equation. And this Voigt fraction correlation usually coming from the experiment measurement. We can do experiment like we inject the bubble in a vertical pipe, and we inject the bubble with different shape, different size, so we have a different flow regimes. And in each flow regimes, we probably will have a different model to best fit the data in that specific regime. And the model parameter need to be injected because with the change of geometry or pressure or mass flow rate, the parameter need to be adjusted to allow the model to capture the data. Here shows the traditional framework how people develop the causal relation in thermal hydraulic field. Starting from the knowledge base, we will design several different experiments, and then we can collect the data from those experiments. After we collect the data, the most important thing is to understand what is the meaning behind the data. And then we can use this data to support the development of causal model. We can then implement into a simulation for different application purpose. And the main drawback of traditional approach is that after we collect the data from experiments, it takes years to decades to understand how we can use those data to support our simulation. Especially the simulation code will be very different and depend on different degree of averaging. We have a one-dimensional system code, and we also have a three-dimensional CFD code. So that's a challenge for the traditional development when we try to apply the code to a newly designed systems. Another issue of the traditional approach is that usually we first start with the one experiment, and we will feed those data with model A, and then we compare the model A to the second experiment. And when we find the model A did not fit well in the experiment B, what do? We feed another model B. And then the problem is when we take the model B back to the experiment A, the model B is not capture the trend of the experiment A. And worstly, when we have the third experiment, none of the model is going to work. The traditional model calibration process will result in a lot of different models with different forms, which increase the difficulty of model selection, and this is called the model form uncertainty for the traditional code systems. With the recent advanced instrumentation development in the thermal hydraulic area, we collect a lot of different collect a lot of big data from like a PIV or infrared camera. So it is reasonable to apply some machine learning technique like a deep learning methodology to simulate those data and then deliver a good model that can apply in a range of flow regimes. And deep learning, why it is interesting, because it has been proven as a universal approximator. There is no theoretical limit to prevent those models to fit the data. The more data we have, we are expecting the better model performance we will get. So the deep learning-based closure relation, we expect it is competitive when we try to use the code to simulate the new design systems, including new geometry, new coolant, or new system conditions. So the data is very important. Before we introduce the data-driven modeling framework, let's first take a look at the structure of data. First, after we've done the experiment or simulation, those results need to be stored, and then the developer can easily access those results. Then those results can be called data. And then we need to know how to use these results to support our model development. That's called intelligence. And from the data to the intelligence, there's a gap. Usually, this gap is filled in by the human opinion, like based on the physics or the analytical derivation of the equation, we can fit the model to fill in this gap. And now we try to use the machine learning to figure out the underlying correlation behind those data, so there's no human bias in it. And this slide shows the idea of total data model integration, and this is also the framework of data-driven modeling. We including a three-part. The first part is the data. The data including the knowledge from expert opinion, and we need to have the experiment with uncertainty, or it can be a high-fidelity simulation like a DNS. And also, we need to store the closure model from the previous experiments because we don't want to abandon the previous efforts. And those results, we call it data, need to be stored in one place. And the second part is the simulation plot. We need to have a reliable simulation platform so the physics can focus on model development while the mathematician can deliver the numerical software which has been validated. And in the middle part is the most important part. We need to have a method to connect the data and our thermal fluid models. That is the machine learning method we will introduce in this work. So before we introduce the framework, let's take a brief look at the technical background, how we can achieve this data-driven approach. To achieve the data-driven approach, we need to have the knowledge from three different fields. First, we need to have the knowledge of thermal fluid models, and we need to have a knowledge of system simulation. And to connect to the system simulation and the thermal fluid model, we rely on some data science method. First, we are look at the single-phase flow modeling. In the single-phase flow modeling, we have a mass momentum and mass momentum conservation equation. And usually, we need to use the Boussinesq hypothesis to approximate the Reynolds stress modeling. And in the Reynolds stress model, like this turbulence viscosity is a potential candidate that can test the data-driven technique. For the two-phase flow simulation, we have a mass momentum and energy conservation equation. And we have a lot of we need a lot of different closure relation, like interfacial information, and we also need to have a drag force information, which I circled in this slide. And the two-phase modeling can be also use a mixture model, which reduce the mass momentum energy equation into 3 equations, and also greatly reduce the number of closure relation. So as the initial approach, the mixture model will be a good candidate since including less closure relation, and we can use it to test our framework. The advantage of mixture model is that starting from the 3 equations, we can capture some flow patterns. If the flow structure becomes complex, we can increase the number of equations. And when we increase the number of equations, it requires more closure relation, but we are able to capture the flow with more complex structure. And the second stage is that we need to have a reliable simulation platform, which is open source, that allow us to program and test our idea. So in this work, we select a system platform. It's called a Dymola. It provides a causal modeling feature, and including a lot of different numerical methods. So our job is focused on developing the model instead of implementing the numerical methods. The second part is OpenFOAM. OpenFOAM is a CFD code. The reason we want to use it is because we are expecting the future system code should be multidimensional. And OpenFOAM is an open source, non-proprietary software. It allows us to implement our model, and we can test our method when we have a multidimensional models. The last part is the NRC trace, which can be used for generating the data that can help us to evaluate whether our framework is working or not. And the third part is the data, which is the most important part. All we are doing is about the data. So we need to understand what is the structure of thermal fluid data. The thermal fluid data can be separated into 3 parts. The first is the different type. We have a global data, local data, and the film data. The second part is the data could come from different sources. It can come from experiment or come from the simulation. The last part is data will have different qualities, and the qualities are determined by the quantity and uncertainty. Now, since we have the data and we have the model, the last step is we need to understand what is machine learning. In the machine learning, we are interested in this work is called the supervised machine learning. In the supervised machine learning, we need to specify what is the input and what is the output for the algorithm. So we need to input some information, and then we need to provide the machine some targets. Then the learning algorithm will correlate the inputs and outputs automatically, then deliver our thermal fluid closures. Currently, there are 5 branches of machine learning algorithm. There are like a symbolic method, evolutionary method, and an analogizer method, and a connectionist method, and a Bayesian method. What we are interested in this work is connectionist method because it provides a non-parametric modeling. It allows us to capture as many as a substantial amount of data as possible. So this is a picture showing that the performance of a different neural networks model and the traditional learning algorithm. When we increase the amount of data, we can see that the traditional learning algorithm like a Gaussian process regression or logistic regression will saturate at some point. So when we increase the data, the performance will not increase. The performance of the model, meaning that whether the model can accurately predict our results. And because the neural network method is a kind of non-parametric modeling, we can design the structure to have a medium neural network or large neural network. And depending on the amount of data we have, if we have more data, then we can design a large network to capture the trend of the data. The deep learning is essentially multi-layer neural networks. Any neural networks more than 2 layers can be considered as deep learning. And we have a 2 basic structure of deep learning used in this work. First, this is called feed-forward neural network. It is very straightforward, like from the input to the output, we have many different hidden layers in the middle. And inside those hidden layers are essentially nonlinear regression functions that allow us to capture the trend of data. And the convolutional neural network is good to extract information from image. So when we have the infrared camera from the measurement, it is like a 2-dimensional colorful image. So we can use this convolutional neural network to capture the feature from those images. And here shows the mechanism of how the algorithm solves the neural network problem. Like starting from the input, we will input some information to the networks, and we can have a model output. And then we can compare the model output with our measurement. Then we obtain the error. Then we propagate this error from the last layer to the previous layer. Then we can use gradient descent method to update the model parameter inside these networks. So the neural networks method is like optimization, and we require a lot of different optimizers to help us to solve the neural network model. And this figure shows that the different optimizer will have a different convergence speed. So depending on our problem, we might want to choose a different optimizer to help us to solve the problem. And this slide shows several different common optimizers. The most common method is the stochastic gradient descent method. We can see that as we approach the local minimum, it's hard to converge because it will oscillate large magnitude. So people implement the momentum method. That help is like as we approaching the local minimum value point, the oscillation will be suppressed, then it will accelerate the convergence speed. And the most popular algorithm is called the Eldon algorithm, adaptive momentum estimation, that is widely used when we try to optimize deep neural networks. And there are several contemporary works that apply the machine learning method to solve the thermal fluid problems. And so we can, from the table, we can see that the previous work, they usually use the DNS data to inform low fidelity model that could be Reynolds average Navier-Stokes equation, or it can be two-fluid models. And now we are going to introduce the data-driven modeling framework. The left-hand side picture shows the traditional framework, and the right-hand side picture shows the data-driven modeling framework. The most different part is that after we finish the experiments, and we don't need to spend years to decades to understand the meaning behind those data. From the experiment to the machine learning-based model, we just need to specify what is the input flow feature and what is the expected target that we want. And the rest of part can rely on the learning algorithm to figure out the underlying correlation. Then we can implement those correlation into the simulation. And depending on different requirement, data and knowledge requirement of using machine learning in the thermofluid problems, we are classify 5 different type of frameworks. And the criteria are given in this table. The first criteria is the PDE equation involved in thermofluid simulation? By this criteria, we can separate the type 5 machine learning from the other 4 type. Meaning that the type 5 machine learning will have no physics constraint inside. All we need is data. So when we feed in the data, we get the answer. It's like an end-to-end learning. The second criteria is the form of PDE given? By this criteria, we can separate the type 4 machine learning from the other 3. The type 4 machine learning are aimed at reconstructing the form of equations. So this is different from the previous 3 type. The third criteria is the PDE involved in the training of closure models? By this one, we can separate the type 3 machine learning from the other 2. The last one is scale separation assumption required for the model development. By the last criteria, we can distinguish the type 1 machine learning from the type 2 machine learning. And now we are introducing the type 1 machine learning framework. This is a simplified framework, and the actual framework will be more complex because we have potentially a lot of different selection of flow features. And these frameworks just want to emphasize what is the role of machine learning in our study. And starting from the element 1, we need to collect the data, could be either come from the experiments or high fidelity simulation. And then we need to average data depending on our problem. The element 3 is like we need to select several flow inputs. And then the element 4, we need to tell machine what is the targets, meaning that what is the expected outputs. After we have elements 3 and 4, we can inject the result into the element 5. We can select a learning algorithm to fit, to build a correlation between the inputs and the outputs. And the element 5, we have a lot of different choices. We can use like a deep learning, or we can use a traditional learning algorithm such as Gaussian process or Bayesian regression. Depending on how many data we have, if we have like a few data, then probably Gaussian process or nonlinear regression will be fit our problem. But if we have like millions of data points, then we probably need to use a deep learning method that can better capture the trend of data. And after we deliver the machine learning-based closure model, we might need to apply some physics constraint to those models because those models cannot violate our physics assumption. But the element 6 is not essential depending on what problem we are doing. And in the element 7, we need to implement the machine learning-based model into the conservation equation, and then we can iteratively solve the problem. Please feel free to ask questions if you have. And next, we will introduce what is the type 2 machine learning. In the type 2 machine learning are designed for the simulation. So in the first step, we need to have a low fidelity simulation. And the low fidelity simulation is not accurate enough to our problem. So we need to calibrate using a high fidelity simulation. And the element 3, we need to pre-process the data because we need to make sure the dimension of a high and a low fidelity simulation are in the same order. The element 4, again, we need to select the flow feature. The element 5 is like we need to define what is the different discrepancy between the two models or what is the expected output of our closure model. And we can use the machine learning algorithm to build a correlation between the inputs and outputs. And the type 2 machine learning is very different. After we obtain the closure model, it is not iteratively solved with the equation. Instead, it is using a low-fidelity simulation to calculate the input for this machine learning-based model, and the output will be a fixed film, and then we implement this fixed film into our conservation equation. So the limitation of type 2 machine learning is that the low fidelity, the solution of low fidelity model cannot be far away from the true solution. Otherwise, we may have some convergence issues. And the type 3 machine learning, we don't need to have the a scale separation assumption. So at the element 1, we can collect the data from either a simulation or experiments. And we preprocess the data depending on whether we need to do some averaging or not. And the element 3, we only need to prepare the outputs or the targets for the machine learning-based model. Because the type 3 machine learning, the training process, including the solution of partial differential equations, and the model inputs is coming from the solution of those partial differential equations. So when we need to prepare the targets for the machine learning model, and initially we have some guess about the value of flow feature, then we take those guess value into our machine learning model to do some optimization process, then implement this closure relation into a conservation equation, and then we compare the solution with the data. If the solution is not converged to our data, then we need to redo the element 4 and then go to element 5, element 6 until the process is converged. And finally, we can obtain the conservation equation with a machine learning-based closure relation inside for the prediction. The type 4 machine learning is aimed at reconstruction. So at the stage 1, we need to collect the time series data. And at the element 2, we need to build a library including a lot of different candidate terms. We take the Navier-Stokes equation, for example. This will prepare the term like diffusion term and the derivative term or the constant term. And then we can do the sparse regression method to figure out what is the coefficient in front of those terms. Eventually, we can find out a good combination that allow us to reconstruct the original Navier-Stokes equation. The last type of machine learning framework is end-to-end machine learning. There is no physics information inside. All we need is collect the data and input into the machine and let the machine to deliver the output for us. We can see two applications. The one is like solving the Schrodinger equation. We input the two-dimensional electric potential, and we can bypass the solution of Schrodinger equation and connect it the electron energy directly. And the second part is like a cross-match DNS method. We can input the cross-match solution into the machine learning model, and the machine learning model will tell us what is the error phi-mesh solution. Then based on this error information, we can obtain our solution. So in summary, the different framework will have different requirement on data and the knowledge. For the type 1 machine learning, the knowledge is high because we need to know how to properly design the experiment that allow us to obtain the closure relations. So the data requirement is low. And the type 2 machine learning, the requirement is not as strict as the type 1, but we need more data to allow us to deliver the model. For the type 3 machine learning, we even need more data to allow the framework to figure out what is the accurate closure relations. And the type 4 machine learning, we require more data, but less knowledge, because at this stage, our goal is to reconstruct the equation. We no longer worry about the closure relation. And the last part is the type 5 machine learning. The knowledge is very low because we don't need to know any physics knowledge about this application. Instead, we just need to feed in a substantial amount of data and rely on the learning algorithm to figure out the correlation. And this figure shows the summary. Our top goal is try to maximize the predictive capability of thermal-fluid simulation and the different type of machine learning frameworks and solution algorithm to approach our top goal. And depend on different assumption, different requirement and knowledge on data, we can select different framework to attack our problems. And here just a summary of contemporary work can be classified into these 5 types of machine learning. And the application including single-phase turbulence simulation and two-phase flow simulation. And we also have some application on like discovering the function form of the Navier-Stokes equation. And I will show some application. The first application is that for the system simulation. In the system simulation, we have a heat exchanger. And here involve the boiling phenomena. We can implement a different like a boiling model inside here to allow us capture allow the system simulation to capture the data. And the second simulation is a CFD simulation. In a CFD simulation, the most important part is what is the correct turbulence model to allow us capture the data. So we can use type 2 machine learning to capture different vortex inside the CFD channel. And the last example is like we can use like a type 3 machine learning framework to figure out what is the nonlinear conductivity inside this temperature field. This is like we can use infrared camera to measure the hot surface. And the purpose is to find out what is the accurate nonlinear conductivity model to allow us to capture the temperature distribution inside this field. And next, I will introduce some issue of deep learning-based model. The deep learning is attractive. However, there are several issues we need to be solved to deliver a model with confidence. The first question is, in the deep learning-based model, there are a lot of different weights. Initially, it is randomly initialized, and the way we initialize those weights will affect our result. The second one is how can we regularize the parameter to increase the predictive capability. The third question is what is the uncertainty due to different network structure. And then how to increase the training accuracy for the neural network while we're using multiple data sets. In the next slide, you will see that when we increase the number of data points, the network are not necessary to give us a good performance. The last question is, what is the criteria to search the optimal deep learning-based fluid closure for the film equations? The neural network with a different weight initialization will result in different performance. For example, the left-hand side picture shows a network, and the blue circle part is the training part. It fits pretty well, but we can see that in the prediction domain, especially in this part, it's not fit very well. And the right-hand side is another network with a different weight initialization. In the training part, it does not perfectly fit our data. However, in the prediction domain, it can fit the data well. And the second question is how we can properly regularize the parameter during the training. The right-hand side picture shows no regularization. In the training domain, it is okay. However, in the prediction domain, we can see that it is disagree with our data. And the right-hand side, with the regularization, we can improve the predictive capability in the prediction domain. And the first question is that the uncertainty due to the neural network structure and the different data sets. We can see that the left-hand side picture shows the performance of the neural network with different structure. The neural network with less structure tend to converge fast. However, the neural network with a large structure may have some difficulty to converge. And the fifth question is like the uncertainty while using multiple data sets. We can see that the black dashed line is when we use just one data set to train the model. It can quickly converge to a small value as we want. And the black dot line shows that when we increase the training data set to 9, we have a difficulty to converge the training results. So at this point, we need to implement the different structure of the neural network to allow the network can achieve the small convergence value. The last one is we need to define what is the criteria to search the optimal deep learning-based fluid closure models. The deep learning model is non-parametric. We can freely decide the structure by using 2-layer, 3-layer, 4-layer, and we can increase the layer to many layers. And for the commercial application, like GoogleNet, they are using like more than 100 layers. So how do we determine the optimal structure for the fluid dynamic closures? That would be very important issues. So in conclusion, the current study shows that deep learning can assist the development of data-driven thermofluid models. It allows the cost-effective model developments, and we can use non-parametric models to capture underlying correlation behind a substantial amount of data. And we also classify 5 different machine learning frameworks that allow us to use in the thermofluid simulation depend on different data and knowledge requirements. The last one is like the type 3 frameworks. We can build a causal relation without a scale separation assumption, so it has the highest potential in extracting the values of big data in the thermohydraulics research. And also it ensures the data model consistency. And let's review what is the data-driven modeling compared to the traditional framework again. The traditional framework requires a lot of human efforts to understanding the meaning behind those data. Then those data can be used to support model development. While we use the data-driven approach, from when we collect the data from experiment, the machine learning algorithm can allow us quickly find out what is the correlation between our input flow feature and our output targets. And depending on different data and knowledge requirements, we can imply different machine learning frameworks to achieve our goal. And one of the important future work is how do we quantify the uncertainty of the deep learning-based causal relations. The deep learning causal relation will have a lot of different hyperparameters, and also the data could come from a different degree of uncertainty. So this is the training of a neural net model. The black dot is our data point. So we can see that the location when we have data, the uncertainty is small, and the shadow part are showing the uncertainty. So for the region we don't have data, or the data is not as dense as the middle part, we will have a large uncertainty. And how do we regularize those uncertainty will be an important work in the future. Thank you very much. Do you have any question? Yes.
I have a quick question about regarding the application.
Mm-hmm.
You've shown me a few slides. Can you talk a little bit more about it? Because it's hard for me to relate the application to the theory.
Okay.
What you were showing there, and
Yeah.
how did the deep learning
Okay.
get involved?
So one of the application is using the CFD simulation. In the CFD simulation, we are solving the Navier-Stokes equation, and that case is a single-phase flow. So we only involve mass and momentum equation, and the only subgrid scale physics model is that the turbulence model. For the deep learning method, we can use the data and directly construct the turbulence model. Then we can bypass using the Boussinesq hypothesis for this random stress term.
Okay, so you're talking about the two figures you're showing, right?
Right,
One is
right.
CFD, the other. So actually, the bottom figure or the plot
Yes.
was generated using the model came up.
Oh, actually, that two figures are the same plot, but the bottom is a stringwise velocity plot, while the top figure is a velocity plot. So they are the same plot, and they are all using deep learning-based random stress.
Oh, okay. Those
So
are already the results.
right. It's already a result.
You're showing a comparison.
No, they are all the results.
Okay, all right.
Yes, and for the two-phase application, in a two-phase application, we would need a correlation like a Fourier fraction. And for that one, usually the Fourier fraction, people will use the Zuber-Finlay correlation. And this correlation fit very well, but there is a distribution parameter need to be adjusted based on different geometry, pressure, or mass flow rate. And what we did is we take the original sleep quality correlation and we implement a sleep factor that will be replaced by neural networks. So we can feed in data with a range of flow regimes. So we don't need to change this change this model based on different flow regimes.
So usually when you have a set of data and let's say you experimented it or simulations, trying to come up with some quotient model, right?
Right.
Do you take the original existing model as the prior knowledge, or you just don't completely?
Usually, yeah, it depends. If we have a rich data coming out from different flow regimes, then we probably don't need a previous model. We can directly assimilate those data and then construct a new model. But if the data are limited in some flow regimes, then the previous model becomes very important. For the region we don't have much data, and we can use those correlations to generate some data to help the model in predicting the flow in those regions. Yes.
So it actually, from my understanding, requires a lot of experience. So when you have data and then you first need to decide where you are, and then you choose from one of the 5 types.
Right.
Right?
Yes.
And then depending on the data, and then in this case, in the case you just mentioned, you have to decide how much we need to borrow from the existing knowledge base.
Yes.
So that really comes to the point that you have to really know this. This is not some black box. You just throw data in and they'll give you some results.
Well,
I
right.
understand the mechanism of the data itself is that it can be seen as a black box.
Right.
But then you need really a lot of knowledge, before you can do this properly.
Yes. That's a good point, because we are doing a physics simulation, so we still the model can be constrained by some physics knowledge that will increase the predictive capability in our engineering analysis problem. Yes, so we.
But your conclusion is type 3 is maybe the best candidate for application.
Right, because in the thermohydraulic simulation, the scale separation could contribute a large error, depend on different problems. For example, if we take a look at the Newtonian flow, the viscosity model is a microscopic dynamic property. And usually, for the Newtonian flow, it is independent of the velocity, flow velocity, which is the global property. But for the non-Newtonian flow, that viscosity model could correlate it to the velocity. So in this case, we cannot separately train that viscosity model and then put it back to the equation because that will cause the data model inconsistency. And in this case, the type 3 machine learning will have the advantage. But for the problem that the scale separation is valid, probably the type 1 machine learning will be good because it will cost less. Yeah.
Any more questions, Chih Wei? Thank you.
Thank you.
So what is the, probably need to turn this off.
Oh, all right.
The part you were showing for the whole prompt, simulation. What is it? I didn't get that part.
Oh, you mean that is iris reactor.
Iris?
Yeah.
Okay. No, what did you use?